crash course. There are some changes in the schedule for our program. Please stay tuned with the changes. Okay. Today we want to continue our discussion about SVM and also introduce you a new and cool classifier that is called AdaBoost. Okay. So we talked about SVM, but now we want to know, could we apply SVM for regression or not? Okay. In linear regression case, in case of linear regression, we know that the cost function is this is a squared error between the prediction and target values plus regularization term, which could be, in this case, it is reach regression. Okay. And similarly, if we want to have a sparse solution for W's, we could use some kind of error function that we called epsilon insensitive error function. Just note that when we had SVM in support vector machine, actually we had some sparse vectors, because just for reminding, let's say if we have lots of data like this, the support vectors are just this one, maybe this one, and this one. So in presence of lots of data, the number of vectors, support vectors, are very low. So in other words, they are sparse. Okay, so if we want to somehow convert linear regression to SVM case, we should somehow convert it to have a sparse solution. Okay. So what is epsilon insensitive error function? It means that we have zero error if the difference between the prediction and target value is less than epsilon. One example is that for this function could be zero when y of x minus t is less than 0, is less than epsilon, and it is y of x minus t otherwise. Okay, and if we draw this error function, it is something like this. So in this region it is 0 because the difference between y and t is less than epsilon. After that it will increase linearly. Okay, so in this case we could rewrite the error function as sum over epsilon insensitive error function of y of xn minus tn plus regularization term. By convention, when we write the error function in this way, instead of using lambda like reach regression, we use inverse of regularization parameter and use it in the loss function term. We call it C. Okay. So it means that if it is like we have a tube around the target values. So if this is the target values, then we have a tube around that. And actually we could rewrite this with introducing slack variables. As we mentioned in the previous session, you could, for making concise some conditions, you could introduce some slack variables. So in here we could write Tn is less than y of xn plus epsilon plus zeta n, because in here these are the points in tube, but we have some data points in here. So for data points in here, we introduce this slack variable. And also for this side, we could write it is greater than y of xn minus epsilon minus another slack variable, zeta hat. Okay, so if we have data point in here, then for this region we know that it is greater than 0 because this condition is active, is kind of active. And so this is 0, and in this region inside the tube we know that both of these slack variables are 0, and in this region this is greater than 0 and this is 0 because this is for making lower bound on Tn. Okay. Okay. Now, so for support vector regression, we could write the loss function as zeta n plus zeta hat n plus 1/2 norm of w squared. So as you could see in here, this term comes from this term. Okay, and with introducing slack variables, now we want to minimize this function subject to that these are greater than or equal to 0. So as we talked about the optimization of this kind of function last session, you could write KKT condition in order to derive some condition and make the problem easier, and you could solve the problem. So this is called SVR, or support vector regression. And also in regression case of SVM, you could again use kernel tree to make it non-linear, and this is so cool about that. And okay, let's see an example in scalar. How should you use that in a scalar? Okay, as you could see in here, you could import it from SVM class, and you could use different kernels for SVR, like it is the kernel in SVM. It is the same thing that we had the kernel trick, and so this is the type of kernel that you want to use. And you know, as you could see in here, we have approximately same parameters, and the C is also inverse of regularization parameter. So as you could see in here, it is called epsilon support vector regression. Okay, and as an example in here, you could see how to actually use that. But for maybe it is better to see that in Python for actually plotting the output of the support vector regression model. Okay, now let's see the effect of some parameters in SVR. As you could see in here, I created some data, 20 data in range 0 to 10, and the output values is squared of x of training for this data. So the true function that I'm looking for is x squared. Okay. Now I define a classifier actually regression model with RBF kernel in here, and now define my x of test and then plot them. As you could see in here, these are the data and this is the prediction. As you could see in here, it is really bad. Okay, but if I change it to polynomial and then run it with degree 3 even, as you could see in here, now I have let's narrow down the range. As you could see in here, now I have a very better approximation. So choosing the right kernel is so important when you're using SVR or SVM. So commonly when you use them, when you want to classify or make regression on your data, you should consider them as hyperparameters and test all of them, okay, if it is possible, or just see your data, okay, to get the sense of which kernel. Okay, now let's increase the regularization parameter. If we increase the regularization parameters, means that we want to reduce the inverse of regularization. Okay, as you could see in here, it is a much like simpler model. So if you increase the regularization parameter, it is equivalent to you have a simpler model. Okay, now we want to talk about combining models. Okay, let's say you have L different classifier. Okay, so you trained L different classifier and you want to somehow combine their result. One simple way to do that is just using average of their prediction, right? So it is the simplest way that you could do to take average from all of the predictions. Okay, we call the combinations, this combination of models, committees. Okay, one important variant of committees is known as boosting, that we talk about it in a very few minutes. Okay, now in fact in boosting we train multiple models in a sequential manner. Okay, so we select some classifier, some base classifier, and train each of them based on previous performance of other classifiers. We will see it in detail in a few minutes later. Okay, so in this case they can produce a model that is much better than a single classifier. Okay, an instance, on the other hand, an instance of averaging is, for example, is to select one model to make predictions, and we select that model as a function of the input. So we train some models, and based on the input we select one of them to make the prediction. Okay, and this is the main framework of decision trees that we will talk about that later. Okay, now let's say in actually polynomial regression that we saw that because of averaging, if we have low biased models, we can make accurate predictions. Okay, so if we have low biased models, for example, in our polynomial example for sine prediction of sine function, if we use polynomial with high degree like 15, then it is a low biased models. And if we have lots of them and train them on different samples data sets, then after making average, it could result in accurate predictions. But in practice, we just have one data set, and so what should we do? One way is to use Bootstrap. Okay, what is Bootstrap? In this method, it is very simple thing that just let's say your data set is like x1, x2, and xn. Okay, so you could create a new data set xb that has n samples. So you sample from this data set x n samples with replacement. So some of the values in x of b could be repetitive in x. For example, it could be, and some of them could be absent in that. So it could be x1, 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 x2, x3, or I don't know, xj. Okay, and the number of all of that is n. So the number of data in here is n, the number of data in here is n, so the numbers are equal. So in this case, you could create m different data sets. Okay, so by using Bootstrap, you could create m different data sets. After that, the prediction of, and after that you train your model on each different data sets, then the final prediction is by taking average from the output of your models. Okay, we call this method bagging or Bootstrap aggregation. Okay, so this is a very simple method to combine some models. Okay, let's see an example that how it works. If we have a regression problem and true function, and let's say the true function is h of x, okay, so this is the function that we are looking for, and let's say the output of each model is, we denoted that by y of m is equal to true function plus an error function. Okay, if we take average for based on with respect to input distribution for the squared error value, then it is equal to okay, and by taking average over all models, for all models we know that the average error is 1 over m expected value of epsilon. Okay, so okay, now if this is the actually, if you have m different output models, then the average error is this. Okay, but if you use YCOM as the output value, as the prediction value, then the error of this prediction is expected value 1 over m y of m minus h of x squared, that is 1 over m epsilon m x squared. Okay, and let's say that the error values for different m has 0 mean. So the error values have 0 mean, and they are uncorrelated, means that epsilon m epsilon l is equal to 0 for m is not equal to l. Okay, so in this case we could derive that the error will be 1 over m, the error value of average error. And this is so interesting result. It says that the error of the combining the model decreases with factor m based on in comparison with the average error of the classifiers. And this is so cool. It means that if you want to get very low error, you could actually use lots of models to make it close to 0. But unfortunately, in real-world applications, these assumptions, especially this one, is not hold. In fact, the errors are highly correlated in real-world applications. So the E of combining models is actually still, it is better or equal to the error of average classifiers, but it is slightly better. Okay, not very like it is not decreased by factor of m. Okay, so this is bagging, and now we want to talk about boosting. So in boosting, as I mentioned, we train our base classifiers in a sequential manner. So in bagging, we just trained our classifiers independently, okay? But in boosting, we trained them sequentially. In here, we talk about a special case of boosting methods. It's called AdaBoost. It is the short term of adaptive boosting, and it is a very popular classifier and strong classifier for classification. Okay, so in here it says that, okay, if you have some base classifier or weak classifier that are slightly, their results, their performance are better than random prediction. So let's say when you have balanced data sets, so if you have balanced data sets, then for prediction on a new test, if you tell me it is 50-50% that is class 1 or class 2, it is a completely random. But if you have a classifier that its performance is slightly better than just predicting random, because predicting random is like just using a coin. Okay, so in case of balanced data set, if you have a fair coin, a random prediction means that you just flip a coin, and if it is head, then you say that, okay, my prediction is that the test data belongs to class 1, otherwise belongs to class 2. Okay, so this is just a random thing. It is not actual and useful classifier. But if you have a slightly better classifier, that its performance is slightly better than 50%, it could be 55 or 60% performance, then these classifiers, you could use some of them to create a strong classifier from these weak classifiers. Okay, so we call this method AdaBoost. It is a special case of training how to create this strong classifier based on these weak classifiers. Okay, in fact, for training strong classifier, first we train a base classifier, then we see the data that this base classifier is wrong in them or misclassified them. Then for the next classifier, we increase the weights of those data and again train another classifier. Okay, and after that we use the weighted vote of all of these classifiers to make the prediction. This is the sign function. So if this is positive, then our prediction is positive, means that it is class 1, otherwise it is class 2. Okay. Okay, so just for getting visual intuition about that, let's say we have some data like this. Okay, so if you want to use AdaBoost for classifying these data, at first it trains a base classifier. So probably you will end up with this decision boundary. Okay, so this classifier misclassifies this data, this one, and this one. Okay, so we increase the weights of them, so you could, for increasing the weights of them, you could actually make them bigger to show that they have now bigger weights. So now training the second classifier. So if we train the second classifier, we will end up with something like this probably. Okay, because now the classification between these are important. Okay, so we classify the second classifier is something like this, and after that we combine them using some weights. Okay, so the final prediction is in coefficient times the prediction of this classifier plus and the coefficient times this classifiers. Okay, this classifier, then we just get the sign of sum of them. Okay, and if you probably draw the final decision boundary, you will end up with this. Okay, so this is the final decision boundary that you could see that the classifiers could classify all of this data correctly. Okay, so the algorithm for learning this this coefficient, actually, if you want, you could read that from the book. It is not so complicated, so it is just an algorithm, but it is not very important for us, but you should just have the intuition behind AdaBoost, and probably you note that it is very prone to overfitting, because in as you could see, it splits the space very quickly, so it could classify lots of data, okay, with 100% accuracy in training stage, but you may end up with poor accuracy in the test stage. So now let's see how to use that in Python and with a scalar. So as you could see, this classifier that use some other classifiers called ensemble. Okay, so in here you could see it takes some parameters. So as the base classifier, you could use different kind of classifiers, and this is the number of classifiers, number of base classifiers that you want to use. And okay, so in here you could see an example from how to use that. As you could see, it is pretty straightforward. Like other classifiers, you just import that from scalar.ensemble and you just fit the classifier on your data. Okay, and as you could see here, the prediction score is 98% accuracy. So this classifier is actually very strong classifier, and maybe it is better to see decision boundary of this classifier. Okay, as you could see in here, it is a very good example of in scalar for plotting the decision boundary of AdaBoost classifier. So as you could see in here, this is the decision boundary of classifier, and so as you could see, it is pretty strong classifier. If you wanted to classify that with SVM, then you will probably will not get a good performance, because I don't know, at least I don't know any kernel to fit to this kind of data, okay, at least intuitively. Okay, so for this kind of problem, AdaBoost is very good classifier, but just you should know that it is very prone to overfitting, especially if you use lots of number of estimators or number of base classifiers. Okay, now you know about AdaBoost, and just maybe it is better to write the classification methods that we learned about them. So until now we learned about logistic regression, SVM, and AdaBoost for classification problem. Okay, so we will see other classification methods in next sessions, but if you have question that when should you use each of them, it is really depends on your data, but also depends on the number of your data. Okay, some of these methods have high computational complexity when your number of data is really large, so you could take care of that. Okay, I think it is enough for today. That I hope that you enjoyed from this session. See you in the next sessions. Bye.